time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging gate contest engineered to give you an experience like none other.
Where you put your knowledge to test
and battle it out with the best.
To bring out the best in you, Unacademy Combat is the most competitive, gamified contest for gate till date, with the best of the questions by best educators.
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack gate deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate gate challenge. Unacademy Combat. Register now.
Okay, guys. Okay, audio is not coming. I think it will come now. Yes, mic was not attached. Yes, yes, yes. Uh, Hello Anurag, thanks for the information Anurag. Okay, so मैं फिर से start कर देता हूँ. I was telling you that my master's is from IIT Delhi, BTech from Jamia, All India rank 226 in 2011. 4 times I have qualified GATE, 7 years of teaching experience and 2 years of industrial experience. 50% से ज़्यादा सब्जेक्ट्स मैं आपके कवर करता हूँ. ये हमारा ऑफिशियल टेलीग्राम चैनल है एंड हमारे बहुत सारे कंटेंट अवेलेबल है अनअकैडमी स्पेशल क्लासेस पे, अनअकैडमी प्लस पे, बट स्टिल वी रिकमेंड आवर लर्नर्स टू गो फॉर आवर प्लस एंड आइकॉनिक प्लान बिकॉज यहाँ पे आपको डेली लाइव क्लासेस, वीकली टेस्ट, स्ट्रक्चर्ड कोर्स, अनलिमिटेड एक्सेस टू दी कंटेंट, रैंक इंप्रूवमेंट बैचेज एंड क्रैश कोर्सेज आर ऑल्सो देयर. आइकॉनिक की बात करूँ तो प्लस के सारे बेनिफिट्स के साथ साथ यहाँ पे आपको पर्सनल कोच मिलता है जो कि आपकी स्टडी प्लान करता है, जो स्टडी बूस्टर सेशन रखवाया जाता है आपके लिए, आपके टेस्ट का पर्सनलाइज्ड एनालिसिस किया जाता है. नॉट ओनली दिस, ऑल्सो यू आर गोइंग टू गेट द स्पेशलाइज्ड नोट्स एंड प्रैक्टिस सेट्स अलोंग विद द डेडिकेटेड डाउट क्लियरिंग एजुकेटर. सो अनअकैडमी सब्सक्रिप्शन के प्राइजेस डियर ये हैं. 3 महीने से लेकर 2 साल तक के सारे प्लान्स अवेलेबल है और आइकॉनिक में 6 महीने से लेकर 2 साल के सारे प्लान्स अवेलेबल है. For instant 10% off, feel free to use the code AISH10. And here as well, combat, which is the largest India weekly competition for GATE. तो हमारा अगला combat जनवरी का होगा कल सुबह 11 बजे. ठीक है. अगेन ये कॉम्बैट काफ़ी इंपॉर्टेंट है आप लोगों के लिए क्योंकि इस बार भी 100 लकी पार्टिसिपेंट्स जीतने वाले हैं एक्साइटिंग गैजेट्स एंड गिफ्ट वाउचर लाइक सैमसंग टैब, JBL स्पीकर्स, Amazon vouchers, and they can win up to 100% scholarship. And AIMT test is also there. ये आपका लास्ट टेस्ट है कल 30th of Jan and it will start sharp at 9 AM. सुबह 9 बजे ये स्टार्ट हो जाएगा. ठीक है. एक बार दोस्तों सेशन को शेयर कर दीजिए. नए बैचेस आप देख सकते हो कि ना सिर्फ सिविल में बट मैकेनिकल, इलेक्ट्रिकल, ईसी इन सब में नए बैचेस स्टार्ट हुए हैं और एवॉल्व और रिसेंट बैच में वी हैव स्टार्टेड स्ट्रेंथ ऑफ मटेरियल बाय अभिषेक सर. चलिए तो स्टार्ट करते हैं सेशन को. प्लीज शेयर द सेशन ऑल ऑफ यू. फर्स्ट ऑफ ऑल प्लीज शेयर द सेशन ऑल ऑफ यू. प्लीज शेयर दी. Okay, please share this session. Okay, सभी लोग चलिए स्टार्ट करते हैं डियर. स्ट्रेंथ ऑफ मटेरियल. और मैकेनिक्स ऑफ सॉलिड. है ना, ये दोनों नामों से सब्जेक्ट जाना जाता है. मोस्टली इसको बोलते हैं मैकेनिक्स ऑफ सॉलिड और स्ट्रेंथ ऑफ मटेरियल, SOM भी इसको बोलते हैं. सिलेबस की डियर बात करूं तो सिलेबस में ये है हमारे सामने. इनके कलर कोड मैंने अलग किए हैं बिकॉज आई डू हैव टोटल 4 सेशन और इसी 4 सेशन के हिसाब से मैं इसमें कवरेज देना चाहूँगा. लाइक दीज टॉपिक्स आई वुड लाइक टू कवर इन दिस सेशन. है ना, थोड़ा ऑप्टिमिस्टिक होके मैंने डिवीज़न किया है बट देखते हैं क्या होता है. एंड जो सेशन 2 बजे से है उसमें हम ये 3 टॉपिक करने का प्लान कर रहे हैं. ठीक है, मतलब एट द एंड ऑफ द डे आई एम प्लानिंग टू कंप्लीट दिस मैनी ऑफ टॉपिक्स. है ना, सेशन 1 प्लस सेशन 2 मिला करके हम लोग ये दोनों खत्म कर देंगे. है ना, दिस इज व्हाट आई नो. ठीक है. अच्छा यहाँ देखिए, यहाँ देखिए कल का जो मॉर्निंग वाला सेशन है उसमें हम ये प्लान कर रहे हैं. कल का जो मॉर्निंग वाला सेशन है उसमें हम ये प्लान कर रहे हैं और कल का जो इवनिंग वाला सेशन है उसके लिए हम ये प्लान कर रहे हैं. ठीक है, तो जनरली कुछ टॉपिक्स ऐसे हैं दे आर लिटरली गोइंग टू टेक मच ऑफ योर टाइम लाइक SFD BMD. इसके लिए मुझे एक एटलीस्ट आई नीड एन हाफ एन आवर टू 45 मिनट्स। डिफ्लेक्शन ऑफ बीम में तो मुझे कम से कम 1.5 घंटा चाहिए, ऑल्दो इट इज मैराथन, बट यस SFD, BMD and deflection of beam collectively they will be taking 2.15 आवर, मतलब 2.25 घंटे के आसपास मुझे लगेगा इन दोनों टॉपिक्स को कवर कराने के लिए, ठीक है। तो ट्रांसफॉर्मेशन ऑफ स्ट्रेसेस हाफ एन आवर, सिंपल बेंडिंग इक्वेशन हाफ एन आवर, टॉर्जन हाफ एन आवर, इट्स गोइंग टू बी लाइक दैट, है ना। तो ओवरऑल विद इन 12 आवर वी विल बी एबल टू फिनिश दिस सिलेबस, है ना। 12 से 13 घंटे भी हो सकते हैं एंड ऑल, ठीक है। इट इज 12 to 12.5 आवर्स और 13 आवर्स वी विल बी एबल टू कंप्लीट द एंटायर सिलेबस, है ना। कुछ टॉपिक्स ऐसे भी है विच आर नॉट इम्पॉर्टेंट फॉर गेट पॉइंट ऑफ व्यू, देन उसमें हम कंटेंट अपना लिमिटेड रख सकते हैं, लाइक स्प्रिंग दे आर नॉट फॉर सिविल गाइस। Pressure vessel is also not there in the civil syllabus for gate, although it is there in ESC, but for gate it is not there. So accordingly we will be planning our syllabus, okay, schedule. तो कोई बात नहीं, इनको मैंने लास्ट में रखा है ताकि कल रखा है, क्योंकि आज के टॉपिक्स हम अच्छे से कर लें, और अगर इन केस अगर आज कुछ पेंडिंग भी रह जाता है तो कल हम इनकी कॉस्ट में ये टॉपिक उठा लेंगे, ठीक है। सो वंस अगेन आई एम वेलकमिंग यू ऑल गाइस। ओके, वेरी गुड मॉर्निंग डियर सचिन, and yes I know Sachin is waiting since long and sorry for the delay dear। चलो करें स्टार्ट। So again guidelines are same, no numericals, only theory, okay, no numericals, only theory, but yeah, again I am saying the topics like SFD, BMD and deflection of beams, they cannot be understandable without the help of numericals. So I would try to take 1 or 2 examples in these chapter or in transformation of stresses as well, okay। Morning dear Prakash। चलो चालू करें all of you, शेयर कर दो एक बार फिर से। और अगर आप लोग रेफरेंसेस की तलाश में हो डियर, तो रेफरेंसेस में यू गाइस कैन गो फॉर आरसी हिबलर, और यू गाइस कैन आल्सो गो फॉर गैरे एंड गुडनो। आरसी हिबलर इज आल्सो अ गुड बुक, गैरे एंड गुडनो इज आल्सो अ गुड बुक फॉर कंसेप्ट बिल्डिंग बुक्स, एंड यस वन मोर यू कैन ऐड, इट इज गैरे एंड टिमोशेंको। Almost second and third are same, okay। और E Popov, so these 4 are the good references for strength of material, these 4 are the good references, okay। चलिए अब स्टार्ट करते हैं डियर। So I hope you all are ready, are you all ready? Tell me, स्टार्ट करें। लाइक कर दो सेशन को, थोड़ा सा शेयर और कर दो। आई विल एक्सटेंड दिस सेशन टिल 1:30, है ना। आधा घंटा डिले लेट हुआ है 10:30 से, तो मैं आधा घंटा कंपनसेट करूंगा 1:30, ठीक है। तो करते हैं स्टार्ट डियर। इफ आई एम सिंपली गोइंग टू कंपेयर द SOM with the engineering mechanics, yes, so SOM is the study of internal force and stress induced in a body considered as deformable body, and engineering mechanics is a study of external force and their effect on the rigid body. SOM internal force on deformable body, mechanics external force on rigid body. I hope you all know the difference between the deformable body and rigid body. If the intermolecular distance between the particles are not going to change on the application of load, then the body is known as rigid body. If the intermolecular distances changes, okay, then the body is known as deformable body, okay। Rigid body do not show any strains, they only going to give you rigid body deformation, they are only going to give you the rigid body deformation, whereas a deformable body are going to give you, whereas deformable body, कमेंट ही नहीं दिख रहे मुझे, एक मिनट कमेंट ऑन करने दो, हाँ ठीक है, yes, whereas deformable body on the application of forces, they changes their shape and size. They can be contracted, they can be expanded, their volume can be lesser, their volume can be more. They can show you some transverse lateral deformation and all. So this is the property of deformable body. Okay, so strength of material is all about deformable body, and it's all about the internal forces, and due to internal forces stress induced. Whereas engineering mechanics is just like your class 11th physics, where you find acceleration, angular acceleration, velocity, displacement and all. Okay, you can also say that in mechanics, in rigid body, you are making a net force, and due to that net force it shows you motion. Whereas in strength of material, we try to keep the equilibrium of forces such that the stresses and strain developed in the members. So due to these stresses and strain, these deformable members, these elastic members are able to take the external load. So by considering the action of external load, they are showing the reaction by the form of stretching or shrinking, by contraction or expansion. Okay, so therefore we can also say that SOM is your deformable physics, deformable body. SOM is your deformable body physics, whereas engineering mechanics is your rigid body physics. Okay, got it. So rigid body physics is this, engineering mechanics, and deformable body physics is this, which is strength of material. And rigid body, deformable body, I told you already that here the distance, shape doesn't change, on the application of load. Shape and dimensions or shape doesn't change. Here dimension or shape may change. Dimension or shape may change. Okay, on the application of load. Okay, so the type of stresses. What is stresses? Stresses is developed due to the internal force, and we can say that stresses are internal force over area. Okay, like suppose if I am applying okay, so why we always deal with stress, not pressure? Can we calculate maximum pressure that can take a member, and according to it we can design? Dear Prakash, first of all, you are asking why do we always deal with stress, not pressure? Okay, because pressure is something you are going to apply on the external basis. Okay, and stresses are something which are being calculated on the internal basis. So whenever we are studying the subjects like strength of material, so we literally want to check what is the actual strength of my material. Okay, pressure is somewhat related to your action. Okay, stresses are somewhat is related to your reaction. So when we are studying the strength of material, when we actually want to check how much my material can take, so it's about the internal thing. So that is the reason why we are taking stresses. We are doing the study of stresses, because we have to check what is the ultimate strength of my material. Okay, so that's why the strength of the material is nothing but the maximum stress taken by the material. So what is the maximum stress taken by material? That all the things we came to know from the experiments. Okay, so that is the reason. Whereas if you have to calculate the external forces, the equilibrium of forces, movement of the system, then you are going to work in terms of pressure. Okay, like we used to do in fluid mechanics, in fluid statics. Okay, dear. Okay, sometimes it may happen that pressure, most of the time, if like say, if this is your beam, if this is your beam or any axial member, and suppose over this member, if we have applied some force P, let's suppose we have applied some force P, then this P over area is not the stress. So maybe that stress is equal to magnitude wise P upon area only. But whenever you are going to draw its free body diagram, it may look like this is P, this is also P, just to maintain the equilibrium, and here it is also going to be P only, here it is also going to be P only, and this is acting on this remaining bar. Okay, okay, so that is the case, that is the case. So this P upon the cross sectional area, if this is developed due to the application of external load only. Okay, but sometimes it is not being developed as equal to the application of load. So such things we used to see in subject like theory of failures, that what all are the consequences. Okay, these forces can be different in different orientation, so that's why we have to be more accurate. So more accuracy can be developed in terms of stresses, not of pressure. Okay dear. Okay, what is normal stress? If any stress is coming normal to the surface, like this one, if I am calculating stress here, ये क्या हो जाएगा P upon area, और ये P upon area का जो स्ट्रेस आएगा वो इस क्रॉस सेक्शन के परपेंडिकुलर लगेगा, वो इस क्रॉस सेक्शन के परपेंडिकुलर लगेगा, इसको हम बोलेंगे नॉर्मल स्ट्रेस. एंड व्हाट इज शेयरिंग स्ट्रेस? अगर मैं किसी लेट्स सपोज इफ आई डू हैव ए बार हियर, if I do have a bar here like this which is fixed at bottom, and I am going to apply, and I want to apply a force P here. So due to this what is happening, it will be deformed like this. So I told you, it is a deformable body, dimension changes as well as shape also change. So in normal stresses generally it is the change of dimension, whereas in case of shear the shape changes, rectangle becomes parallelogram, square can becomes rhombus and all. Okay, so here you can check here. So this is the deformable diagram, and if we are going to apply a horizontal force here, so stresses would be generating along this surface. Okay. So here stresses would be how much? Here stresses would be how much? It will be generated along the surface dear. It will be generated along the surface, and it is like how much? So this is the shear stress, and it is actually acting normal to the along the surface. So normal stresses are normal to the surface, means perpendicular to the surface, whereas shear stresses are along the surface. Okay, or you can say tangential surface, isn't it? So this is the difference between the normal and shear stress. So normal is across 90 degree and shear is tangential, okay, along the plane. Okay. Okay, so that is the case. Okay. Now, as I told you, normal are along, normal are across, or shear are along of the surfaces. So this, so what, how we can write stresses in a two dimension? How we can write stresses in two dimension? Anybody? How we can write stresses in the two dimension? Suppose if we do have an element in 2D. So how many normal forces are possible? How many normal forces are possible? Suppose this is let's say normal stress. This is also normal stress. If this is sigma 1, if this is sigma 2, now shear stresses are also possible. So shear stresses are also possible. Shear stresses, if these surfaces will look like this, so in order to prevent the moment equilibrium, so the on the adjacent faces shear stresses would be different. So just this will be counteracting this, and it will be counteracting by this. So the idea is that clockwise couple and net anti-clockwise couple remain same. Okay, okay, but yes, notation would be different. Notation would be different if it is tau. Okay, and face this is y x, then this is tau, the face is x, and it is y. So this is also tau yx, this is also tau xy. Okay, so one shear and two normal stresses are there. If I want to write them in the matrix form, if I want to write them in the matrix form, then it would be sigma 1. Okay, and this would be sigma 2. Like that we can, very good morning dear Shanti. Okay, so like that we can write the stresses in 2D. Okay, हाँ लेट हो गई क्लास आज थोड़ी सी. ओके, चलो कोई नहीं, आज थोड़ा सा लेट हो गया, कोई बात नहीं, बाकी के टाइम पे रखेंगे एकदम. ठीक, चलो. So similarly, if I want to write this stress matrix for 3D, then it will be like this. And for 2D, how we can write, वो मैंने आपको बता ही दिया. So this is the stress matrix for 2D, and this is the stress matrix for 3D. एक बार बता दीजिए अगर सबको कोई डाउट किसी को यहाँ तक. So this is the stress matrix for 3D, this is the stress matrix for 2D. 3D का भी अगर मैं आपको बना के दिखाऊं, then 3D can also be shown like this. So it can also be shown like this. It can also be shown like this. Sound is not clear means, am I not properly audible? Let me increase the volume of my device and check. Not properly audible. What's wrong with sound? Increase the volume. Okay. Try to increase the quality of your video from your device, dear Prakash. एक बार आप देखिए वीडियो, हाँ क्लियर आ रही है, मेरे को भी क्लियर आ रही है. एक बार आप वीडियो क्वालिटी या ऑडियो क्वालिटी इंप्रूव करके देखिए. sometime it is going to be mute, that is okay. I am making sure if it is a mute due to some disturbance, then I am not speaking at that time. It is I am not speaking anything in during that time, that is okay. Okay, anybody will help me that how can I set the value of shear stresses here? Anybody, what is this stress? Tell me, what is this stress? Out of this, what is going to be this stress? Tell me. कितना होगा ये? Yes, Yashwin had said sir tau yx. Okay, here face is y and direction is tau xy. Prakash is saying it should be tau yx. It should be tau yx. Face you check. Face is upside, means along the y axis, and arrow direction is towards x side, in x direction. So first notation is a face, and second notation is of direction. Second notation is of direction. Okay. Similarly, if I am doing it like this, this is dear tau, face is x-axis, along the x-axis, and direction is y-axis. And need not to say again and again that tau xy is equal to tau yx. Clear? Similarly, if I am talking about this, you can say this value. So can anybody tell me what is this green one? What is top green one? What is this green one? Top वाला जो है वो कितना होगा? Top वाला बता दीजिए. What is there top वाला? Tell me. Tau yz. Yes sir, Yashwin, very good. It is tau yz, and it would be how much? It would be tau zy. So again tau zy and tau yz are same. Again these are same, dear. Yes, correct, Anurag. Yeah, tell me this black one. Tell me the black one. And this is yx actually. This is yx. xy. Okay. Let it be like this only. Don't worry. Because they both are same, na? Yes. So as Anurag and Yashwin Sachin, they said that it is tau zx. So it is face is Z and they are going towards X. Similarly, here face is X, they are going towards Z. So tau XZ and tau ZX are same. So you can see this is XY, this is YX. So YX and XY are same. So they have written same thing here. This is XZ, this is ZX. So they are same. We have written same here. This is YZ, this is ZY. They are same. We have written same here. Okay. So this stress matrix is symmetrical. What is symmetrical matrix? If we are interchanging rows into column and column into rows, then whatever matrices we are getting, that matrices are known as symmetrical matrix. So stress matrix are symmetrical. Similarly, you can check it in 2D. It is XY and it is YX. So, but both of them are same. Okay. So they are same because tau YX and tau XY are same. So it is also symmetrical. Are you getting the point or not? Are you getting the point or not? Tell me. So if somebody asks you in interview or in an exam that why this stress matrix is symmetrical, so you have to say this stress matrix is symmetrical due to the moment equilibrium. We have to maintain the moment equilibrium of a system of particle. So in order to maintain that, the net moment in that system must be equal to 0. Like net force in the either direction should be equal to 0. Okay, so stress matrix is in equilibrium due to the moment equilibrium here. It is due to the moment equilibrium. Okay. Okay. Now next is strain. Any doubt so far? Any doubt to anyone so far? Please let me know. चलो आगे बढ़ते हैं फिर आगे बढ़ते हैं नेक्स्ट इज स्ट्रेन डियर व्हाट इज स्ट्रेन व्हाट इज स्ट्रेन स्ट्रेन हिंदी में बोलोगे तो क्या होता है तनाव ओके सो व्हेनेवर द डायमेंशन ऑफ ए डिफॉर्मेबल बॉडी चेंजेस इट लीड्स टू स्ट्रेन okay strain may be in the longitudinal direction it may be in the transverse direction it may be the volumetric strain and all okay so all such things are leading towards the strain okay so strain is a change in the dimension with respect to the original dimension it is with respect to the original dimension so if I want to write the general definition of a strain so simply you can write it is a change in dimension with respect to the original dimension okay are you getting the point or not so again like of stresses strain can also be of two types one is normal strain and another is shear strain one is normal strain another is shear strain what is normal strain normal strain is just like your longitudinal strain and shear strain is your tangential strain it is your tangential strain सर हिंदी में स्ट्रेन को विकृत कहते हैं अच्छा विकृत क्या बात है सचिन बढ़िया स्ट्रेस से मुझे पता है स्ट्रेस इज तनाव स्ट्रेन इज विकृत चलो नई चीज पता लगी अच्छा तो ये लॉन्गिट्यूडनल विकृत क्या होता है लॉन्गिट्यूडनल विकृत क्या होता है सपोज दिस इज some stress and due to this dimension get changes so it is going to increase like this अरे नहीं यार न्यू हरकत नहीं आज कंघी कर ली बस वही चार बाल है कभी इस साइड कर लेता हूं कभी इस साइड कर लेता हूं so let's say the original dimension of this bar is L or let's say it is L0 and after this force extension is there. Now it becomes L naught plus delta L. So longitudinal strain is what? Change in dimension with respect to original dimension. But it is shear strain is somewhat slight different. What is there in shear strain? Shear strain में हम क्या करते हैं? Suppose if this is my block and आप लोगों ने यहाँ पे एक नॉर्मल फोर्स लगा दिया और एक shear टेंजेंशियल फोर्स लगा दिया. So shear फोर्स लगाने के कारण क्या हुआ डियर? टेंजेंशियल फोर्स लगाने के कारण क्या हुआ? डिफॉर्मेशन हुआ. अब डिफॉर्मेशन होके ये कुछ ऐसा हो गया. डिफॉर्मेशन होके कुछ ऐसा हो गया. So this is the change in dimension, but this time the change in dimension we have to measure with respect to transverse dimension. Suppose if it is B and this change in dimension is delta, so shear strain is like a change in the tangential direction with respect to its perpendicular dimension. So this is delta over B. This is delta over B. Are you getting the point or not? This is delta over B. Okay. So shear strain, these shear strain we are taking positive, and this shear strain is like negative. Okay, this is as per convention we are taking it positive shear strain and it is negative. Okay, there is one more way to identify positive and negative. So I can also discuss you same here. जैसे यहाँ पे मैंने इस tau yx को पॉजिटिव बोला, क्यों बोला? There was one more logic behind it. And you could have asked, sir, when we have to take positive, when we have to take it negative. Like normal stresses, it is quite clear. If it is going away, we will take it positive, or if it is coming towards, we will take it negative. So compressive stresses we will be taking negative, and tensile stresses we will be taking positive. But these things are not very easy to visualize in shear. In shear, what should be the convention? Anybody? In shear stress, what should be the convention? Anybody? This is xy and this is yx. So both of them I have shown positive. But what is the convention? Tell me. What is the convention? देखिए मैं क्या करता हूं ना, मैं इस क्यूब के एकदम मिड पे जाता हूं. इस क्यूब के एकदम मिड पे जाता हूं और इसको मैं ओरिजिन मान लेता हूं, है ना. ये मतलब मेरा स्टाइल है इसको एनालाइज करने का. एकदम बीच पे गया मैं, तो बीच से राइट वाला डिस्टेंस पॉजिटिव एंड लेफ्ट वाला इट इज नेगेटिव, एंड फ्रॉम द मिडिल ऑफ दिस पॉइंट अप साइड इज पॉजिटिव एंड डाउन साइड इज नेगेटिव, and in this direction it is positive, in this direction it is negative. It is just like that. Okay, this is positive tau yx. Why? Because here the y is the face. Just a minute guys, just a minute. Yes, this is the positive of the face x, because with respect to the center point the face is towards right, so it is positive face. And the direction is also positive of y. It is going in the upward direction. So positive and positive are positive. Had this been like this, maybe like this. So here you could have seen, although the face is positive x, but direction is negative y. So it is minus tau xy. So like that we can define the sign convention of shear stress. Like that we can define the sign convention of shear stress. Are you getting the point or not? Okay, so positive face, positive side, positive direction, it's positive. And negative face, negative side is also, negative direction is also positive, because negative is also positive. Like this is positive yx. What about this tau? It is negative y, and direction is also negative. So minus y minus I x is also tau yx. So like that we can define the sign convention of stresses. अगर strain की बात करनी हो तो strain के sign conventions are also easy. Like what is its deformation? What is its deformation? If I am going to deform it, then it will be like this. Tell me, will it be like this? ऐसा, okay, then it will be this. It will be this. So at this side, this angle is this side. The angle is, let me draw it with some other color. This side the angle is less than 90 degree. Okay, and here it will be deforming like. It will be deforming like. It will be deforming like. Okay, it will be deforming like this. So here you can see that this angle is greater than here the angle is greater than 90 degree. Here the angle is greater than 90 degree. Here the angle is less than 90 degree. So if angle is less than 90 degree, it is positive shear. It is, if angle is greater than 90 degree, it is negative shear strain. Okay, so like this we can conclude the sign convention for strain dear. Tell me if it is clear to all of you. Tell me if it is clear to all of you. Okay, I hope it is clear to all of you. Any doubt in shear strain convention dear? Any doubt in shear strain convention? Anybody? Okay, is it clear, crystal clear? ऋषिकेश, क्या बात है? चलो बढ़िया, आगे बढ़ते हैं. So this is the case dear. Strain matrix is like this. Strain matrix is like this. Like we do have stress matrix na? Like we do have stress matrix. Sigma xx. It is very easy to write stress matrix. First is x x x. Second row is y y y. Third row is z z z. Now transverse it. X x x. Second column is y y y. Like that the third column is z z z. Now the same x-axis is telling you sigma, and cross one are shear. So make it tau here. Make it tau here. Okay, so same thing. Now dear, simply if you want to write the strain matrix based on this stress matrix, then sigma will be replaced by epsilon xx or simply epsilon x in place of tau xy, or simply write gamma xy by 2. Now what is this gamma xy by 2? What is this gamma xy by 2? Suppose this is the total strain. Let's suppose this is the total strain. This plus this is gamma xy. This plus this is, let's suppose initial angle was 90 degree. So it is now 90 minus theta. So gamma is going to be 90 minus theta. And due to the symmetrical or equal value of shear stress developed on these two consecutive adjacent faces, so these angle on the both side are considered to be same. So if they are same, if total deformation is gamma, then on one side what is the deformation? It is gamma by 2. It is gamma by 2. So let me call it gamma xy by 2. Let me call it gamma yx by 2. Like that we can define this. So this is tau xy. So I am writing gamma xy by 2. this is tau yx, I am writing gamma yx by 2 because it is assumed the total this strain, this plus this is the total strain, this plus this is the total strain, and it is 90 minus 5, and this both strain has to be same because same kind of stresses are originated on these two adjacent faces. So these two strains value are also same, but the net strain in this direction is this angle plus this angle, but fortunately both of these angle are same. So see, simply we are dividing these strains into half value. Similarly, tau xz, it is gamma x by z by 2, gamma zx by 2, yz, gamma yz by 2, gamma zy by 2. Okay, so it's going to be like this. It's going to be like this. Are you getting the point or not? Tell me. Tell me, everybody. Any doubt to anyone? Any doubt to anyone? So, what is the total strain in xy plane? Anybody? What is the total strain in xy plane? What is the total strain in xy plane? कितना हो जाएगा? Normal strain is sigma yy, and what is the no doubt, sure. So how you can find the total strain, normal strain? Like this is the total strain in xy plane. This is the total strain in yz plane. This is the total strain in zx plane. I want to explain this with the help of a 2D figure. With the help of 2D figure, we can explain it, dear. Suppose this is the deformation in x direction, let's say u. This is the deformation in y direction, let's say v. So what is the shear stress, shear strain in due to this u? So it is del u over with respect to distance, transverse distance del y. And what is the, okay, थोड़ा सा कॉम्प्लिकेट हो जाएगा, मैं इसको सेपरेटली समझाने की कोशिश करता हूँ. यहाँ देखो, this is the element, and now it will be like this. थोड़ा सा डायग्राम में ऐसे बना देता हूँ. ध्यान दीजिएगा, नहीं आएगा तो पूछिएगा. Let's suppose this is u, this displacement is u, and this displacement is v. This displacement is v. So u is the displacement in the x direction, v is the displacement in the y direction. Okay, and let's suppose this is the x direction, this is the y direction. So along x axis it is u, along y axis it is v. So if I want to check the total gamma, this plus this, what is this, dear? This is del u by del y. What is this one? What is this one? It is del v upon del x. So what is the total gamma? Gamma xy is what? This angle plus this angle. So this angle is del v by del x. This angle is del u over del y. So the total normal strain in x direction is, are you getting the point or not? So it is del u by del y plus del v by del x, and it is equal to gamma xy. Similarly, del v by del y we can write like this. Similarly, del w by del z we can write like this. The same concept you also use in your fluid mechanics, in fluid kinematics. Fluid kinematics में भी आप ये same concept use करते हो, dear, है ना? रेनॉल्ड्स ट्रांसपोर्टेशन थ्योरम लगाते हो and rate of rotation देखते हो वहाँ पे. Are you getting the point or not? Okay, and you use this concept for calculating vorticity, circulation, etc. Okay, चलिए. So this is also important. एक आधी बार आ रखा है क्वेश्चन इससे कि आपको स्ट्रेन इस तरीके से निकालना पड़ गया था. Okay, now we will be moving to stress strain curve. Okay, so what is the stress strain curve for mild steel? It is, you can say, the second aspect of this chapter. What is the stress strain curve of mild steel? So we used to read this curve so many times in our civil engineering. स्टील में भी पढ़ते हो इसको, आरसीसी में भी पढ़ लेते हो, सोम में तो पढ़ते ही हो, और सोम में तो सबसे ज़्यादा तवज्जो भी दिया जाता है. So if I am going to apply the draw the graph between the normal stresses and normal strain, or longitudinal stress upon longitudinal strain, so the graph comes like this. ये ग्राफ बहुत ज़्यादा एक्सेजरेट करके दिखाया गया है, स्पेशली आप कह सकते हो एक्स एक्सिस के अलोंग. एक्स एक्सिस के अलोंग इतना ज़्यादा स्टीपनेस आपको, इतनी कम स्टीपनेस आपको मिलती नहीं है. In practically if you are drawing visualizing this graph with respect to proper scaling, it is like this, it is like this. ओके तो थोड़े से आपको पॉइंट्स क्लियरली समझ में आए, तो इसलिए इसको थोड़ा सा ऐसे लैटरल डायमेंशन में एक्सपैंड कर दिया गया है, इसको लैटरल डायमेंशन में क्या कर दिया गया है, एक्सपैंड कर दिया गया है, ठीक है। चलिए फोटो मेरी तंग कर रही होगी तो मैं इसको थोड़ी देर के लिए थोड़ा छोटा कर देता हूँ, थोड़ा सा छोटा कर देता हूँ थोड़ी देर के लिए, ठीक है, कोई दिक्कत नहीं। अब मैं कोई चीज़ मेरी डिस्टर्ब नहीं कर रही होगी ना, चलो कोई बात नहीं। अब देखते हैं। So this is the points, various points written here, dear. OA, what is OA? OA is the linear curve. आप कह सकते हो till A, it is the proportional limit, or your stress is proportional to strain, directly proportional to strain. It is also valid. So Hooke's law is valid. Hooke's law is valid. Hooke's law is valid. Okay. B is also elastic limit, मतलब आपका जो मटेरियल है वो B तक भी क्या रहेगा, इलास्टिक लिमिट में रहेगा, मीन्स टिल B as well. If you are going to remove your load, then material can regain its original dimension. And like C is your upper yield point, D is your lower yield point. Practically A, B, C, D are nearly same, okay. But still अगर आप माइक्रोस्कोपिक लेवल पे इन चीज़ों को देखोगे, then you can distinguish between A, B, C, A and D. C और D में जो dip है, it is the slippage of carbon atoms, but this dip is not seen everywhere, or in fact upper yield point is not defined for every material. So C and D most of the time they are same only. But if somebody asks you which is the yield point, D or C, then you have to say it is a C. Upper yield point is by default the default yield point. Okay, B is the elastic limit and A is the proportional limit. Till here the Hooke's law is valid. Okay, so we apply stresses proportional to directly proportional to strain here, because we take the appropriate factor of safety, and we always take factor of safety with respect to the yield value. So our working stress comes somewhere here. Okay, chaliye. So upper yield, lower yield. D2E is known as the plastic region or yield plateau. It is known as the plastic flow, or you can say the yield plateau. Okay, and from E to F the strain hardening region is there. It is again the readjustment of the particles structure within the material, and again the material is capable of taking much more stress. Okay, at the cost of more strain it takes more stress. But after E, after F, again it comes down and it got fracture somewhere here. G is the fracture point, D is the fracture point, and F to G zone is known as necking zone. Okay, F में आपकी ultimate value है, G आपका lower value है, ठीक है, और G पे आपका fracture हो गया. This is known as necking zone. Okay. And at G the failure of mild steel happens like cup cone failure. It happens like cup cone failure. So this is the stress strain curve for the mild steel. This is the stress strain curve for the mild steel. So you can see it one more time. ठीक है, मैं दोबारा से बड़ा हो जाता हूँ. ठीक है. So this is the stress strain curve for mild steel. Proportional limit, elastic limit, upper yield point, lower yield point. D2 is the elastic point. E2F is the strain hardening. D2E is the yield plateau for plastic flow. D2E is F is ultimate point strain hardening. Then it is necking. बोला जाता है yield के जितनी देर बाद फ्रैक्चर आता है, मटेरियल उतना ही डक्टाइल होता है. yield के जितनी देर बाद फ्रैक्चर आता है, मटेरियल उतना ही आपका क्या होता है, डक्टाइल होता है ना. इज इट क्लियर? ओके, चलो सर पाई प्लस 0.0005 का क्या मतलब होता है? पाई प्लस पाई बाय 2 होगा डियर, पाई बाय 2 प्लस 0005 होगा डियर. इसका मतलब होता है कि जो आपकी गामा की वैल्यू है, बिकॉज आई टोल्ड यू दैट 90 माइनस थीटा ओके इज इक्वल टू गामा. So 90 minus pi minus 0.005 it will come. So it is minus pi by 2 minus 0.005. This is the value of shear strain. This is the meaning of pi plus 0.0005, but it should be pi by 2, I guess. Okay, so this is the shear strength. So whatever comes after pi by 2, that is going to be the value of gamma. Okay dear सार्थक, देखो मुझे पता है कि विदाउट न्यूमेरिकल चीज़ें थोड़ी सी डाइजेस्ट करनी मुश्किल होती है. अगर ये नॉर्मल कोर्स होता तो मैं डेफिनेटली आपको शेयर स्ट्रेन के ऊपर या नॉर्मल स्ट्रेन के ऊपर उनकी एप्लीकेशन के ऊपर क्वेश्चंस करवाता, ठीक है. और शायद मैंने लास्ट टाइम जब क्रैश कोर्स लिया था करवाया भी था, है ना. बट लास्ट टाइम व्हेन आई टुक क्रैश कोर्स देन आई टुक इट अराउंड 30 आवर्स इन क्रैश कोर्स ऑफ SOM. यूट्यूब पे पढ़ा हुआ है वो, ठीक है. But this time I have to complete it from only from theoretical point of view, क्योंकि पर्पस ये है, जैसा कि मैंने आपको RCC में बताया था, पर्पस ये है इसका कि आप लोगों को एग्जाम आने वाला है और एक वन शॉट रिवीजन चाहिए, ठीक है, थ्योरेटिकल की, थ्योरी की, कि कोई पॉइंट मिस ना हो, तो आप वो वन शॉट रिवीजन इन वीडियोस की हेल्प से कर सकते हो. So this is the meaning of this end game marathon session. Okay. So this is the stress strain curve for mild steel and I was telling you कि ईल्ड आने के जितनी देर बाद आपका फ्रैक्चर होता है मटेरियल उतना ही आपका डक्टाइल होता है, और अगर ईल्ड आने के बाद फ्रैक्चर इमीडिएट हो गया तो मटेरियल आपका ब्रिटल कैटेगरी में आता है, लाइक कॉन्क्रीट. इफ ईल्ड आने के बहुत देर बाद फ्रैक्चर होता है तो मटेरियल आपका डक्टाइल कैटेगरी में आ गया, लाइक स्टील, माइल्ड स्टील. ओके, चलिए आगे बढ़ते हैं. डिफरेंट ग्रेड ऑफ स्टील की अगर मैं बात करूं, सो नाउ इफ आई एम ड्राइंग द स्ट्रेस स्ट्रेन कर्व फॉर माइल्ड स्टील, इट इज कमिंग लाइक दिस. इफ इट इज कमिंग लाइक दिस, it is coming like this. Okay, then what is happening with different grade? So different grade may look like this. Okay, it is Fe250 and let's say it is Fe, let's say it is Fe415 and let's say it is Fe500. Let's say it is Fe500. So all these are the different grade of steel. Let's say this is Fe415, this is Fe500, this is Fe250 or mild steel. So these are known as HYSG steel. As you are going to increase the grade of steel, you can see their elastic limit is increasing. And what about their elastic limit? How we can say their elastic limit? Here there is not a clear upper yield point or lower yield point. So in such material, what you do, you take the help of proof stresses. You take the help of proof stresses. जिन material का elastic limit is not clearly defined, so there we take the help of proof strain and proof stresses. What is proof strain? Proof strain is 0.2% strain, और idea is कि 0.2% strain से you are going to draw a line, okay, parallel to initial tangent. You are going to draw a line parallel to initial tangent, and wherever they are going to cut your original graphs, okay, जहाँ पे आपके ओरिजिनल ग्राफ को टच करते हैं डियर, और वही आपका यील्ड पॉइंट माना जाता है. ठीक है, तो इट इज कमिंग, इट इज so they are cutting this graph here. तो इसको आप बोल दोगे it is 415 and इसको आप बोल दोगे at Fe500. okay, so this strain is how much? This is proof strain and this is 0.0020, 0.0020. So like that we can draw the stress strain curve for different grade of steel. Is it clear to everybody? Tell me, any doubt to anyone? कोई डाउट किसी को यहाँ तक? चलिए, कोई डाउट नहीं. अच्छा, so this is the stress strain curve for different grade of steel. Okay, now based on the stress strain curve we defined several properties of the material. So पहली प्रॉपर्टी यही है कि what is brittle material and what is ductile material. मैंने आपको बताया था कि अल्टीमेट यील्ड पॉइंट आने के थोड़ी देर बाद ही जो फ्रैक्चर हो जाता है उसको हम ब्रिटल मटेरियल बोल देते हैं. बेस्ट एग्जांपल इज कंक्रीट. और डक्टाइल में क्या होता है कि यील्ड आने के बाद fracture happens after so much of large strain. So that is ductile like steel. Okay. And there are several properties of the material. The first one is elasticity. Elasticity is what? It is the property of the material by virtue of which it undergoes to its original dimension. It undergoes to its original dimension. Okay. मतलब ये वो प्रॉपर्टी है जिसमें आपका मटेरियल ओरिजिनल डायमेंशन में आ जाता है आफ्टर द अनलोडेड, और ऐसा होता है अप टू आपका इलास्टिक लिमिट तक. इलास्टिक लिमिट तक अगर आप अपने मटेरियल को अनलोड करते हो देन 100% रिकवरी इज देयर. ओके, बट यस दिस रिकवरी इज डायरेक्ट इन, इट हैपेंस इन डायरेक्टली मैनर इफ इट इज अंडर प्रोपोर्शनल लिमिट. प्लास्टिसिटी क्या है? If permanent deformation left over after the removal of load, then that property is known as plasticity, है ना. सबसे आसान तरीका है, आपने देखा होगा रबर बैंड इलास्टिक कौन बोलते हैं, तो उसको आप लोड हटाते ही वो अपनी ओरिजिनल शेप पे आ जाता है. तो रबर बैंड की जो प्रॉपर्टी है उसको हम इलास्टिसिटी के नाम से ही इलास्टिक बोल देते हैं. और प्लास्टिक पॉलिथीन जो होती है उसको अगर आप डिफॉर्म करोगे तो डिफॉर्म्ड रह जाती है. सो दैट इज ए परफेक्ट एग्जांपल ऑफ प्लास्टिक बॉडी. तो वहीं से शायद उसका नाम प्लास्टिक या पॉलिथीन पड़ा होगा, plastic polythene. Okay. Third one is creep. What is creep? It is the property due to which material undergoes additional deformation, and above that due to applied load with passage of time under sustained loading is called creep. देखो creep में क्या हो रहा है ना, creep में क्या हो रहा है कि अगर मैं यहाँ पे बात करूँ plasticity की, तो plasticity में dear we have crossed the elastic limit. We have crossed the elastic limit, और इलास्टिक लिमिट क्रॉस करने के बाद, लेट्स सपोज दिस इज इलास्टिक लिमिट, वी हैव क्रॉस्ड इट एंड दिस इज योर मे बी अनलोडिंग कर्व, सो देयर इज सम परमानेंट डिफॉर्मेशन. ओके, सो प्लास्टिसिटी होने के लिए आप इन्हें इलास्टिक लिमिट को क्रॉस किया, बट समटाइम इट मे हैपन दैट यू अप्लाइड लोड विद इन इलास्टिक लिमिट. You applied load within elastic limit and still there is some permanent deformation. Okay, and it can happen only if that load is applied here for a very long period of time. ऐसा तभी हो सकता है जब लोड आपका बहुत लंबे समय तक लगा हुआ हो. ठीक है, जब लोड आपका बहुत लंबे समय तक लगा होता है तो उसको रिमूव करने के बाद there is some permanent deformation in your material. This is known as the creep, and these phenomena getting hindered with respect to many parameters like temperature. Okay, amount of loading. No doubt your loading is under within elastic limit, but within elastic limit as well आपका एक लोड हो सकता है 100 किलोमीटर, मान लो आपका इलास्टिक लिमिट है, तो एक 90 आप अप्लाई कर सकते हो, एक 70 कर सकते हो. तो ऑब्वियसली क्रीप वुड बी फाउंड मोर इन केस ऑफ 90 किलो न्यूटन केस. हाई टेम्परेचर पे ज्यादा होता है, साइक्लिक लोडिंग के लिए ज्यादा होता है, और सॉरी सस्टेन लोडिंग के लिए ज्यादा होता है. सो इट इज द प्रॉपर्टी बाय वर्च्यू ऑफ विच मटेरियल अंडरगोज एडिशनल डिफॉर्मेशन ओवर एंड ओवर दैट ड्यू टू अप्लाइड लोड विद द पैसेज ऑफ टाइम अंडर सस्टेन लोडिंग. इट इज नोन एज द क्रीप. कोई डाउट, एनी कंफ्यूजन बिटवीन द प्लास्टिसिटी एंड क्रीप? क्रीप और प्लास्टिसिटी में कोई कंफ्यूजन डियर? टेल मी. Okay, great. So what is fatigue? What is fatigue, dear? Tell me. What is fatigue? Fatigue is happening due to the deterioration of material under the repeated cycle of stress and strain, resulting in progressive cracking. That is eventually produces fracture is called fatigue. So जो आपका साइक्लिक लोडिंग होती है ना, तो इसके होने के कारण जो आपको धीरे धीरे क्रैक्स प्रोपोगेट होते हैं, इस फेलियर को हम बोलते हैं फैटिग. जनरली देयर आर डिजाइंस which are done on the basis of fatigue rather than fatigue value rather than the yield value or elastic value. Okay, normally in civil engineering we prefer elastic value, elastic limit, and for cyclic loading cases we use fatigue value, like for steel only, for mild steel only the yield value is 250, but the fatigue value is taken as 185 or 186. Okay, So under 186, if you are going to apply even a repeated cycle of loading, so your steel is not, your mild steel is not going to show any cracks. Is it clear? Just a minute, there is again a spam. So let me handle this. Just give me a minute, dear. Okay. ठीक है. So this is the fatigue, and there are lot many properties like resilience, toughness, hardness. Okay, malleability. What is resilience? What is resilience here? It is the property of material by virtue of which it absorbs energy when deformed elastically and release it on unloading, है ना. तो रेजिलियंस क्या होता है डियर आपका, कि जैसे आपने ये कर दिया. ओके, सो लेट्स सपोज यू हैव ड्राइंग ग्राफ दिस. So here you can see that it is the resilience up to elastic limit, whatever energy you have stored, that is resilience. In fact, it is the modulus of resilience if it is a stress strain curve. If it is load deflection curve, then it is resilience. Okay, so it is the property of the material by virtue of it it absorbs energy and deforms elastically when releases on unloading. जैसे हम बोलते हैं ना स्प्रिंग का रेजिलियंस अच्छा होता है क्या है कि आप पहले उस पर वर्क डन करके एनर्जी स्टोर करते हो और सारी की सारी एनर्जी आपको क्या कर देता है, वापस फेंक देता है. दिस इज नोन एज रेजिलियंस. अच्छा, टफनेस क्या होता है? टफनेस इज द एबिलिटी टू एब्जॉर्ब मैकेनिकल एनर्जी अप टू फ्रैक्चर पॉइंट. लाइक रेजिलियंस इज योर इलास्टिक पॉइंट, और टफनेस क्या करेगा डियर? टफनेस आपको पूरा का पूरा फ्रैक्चर पॉइंट तक एनर्जी स्टोर करके देगा. अगर लोड डिफ्लेक्शन कर्व है ये तो टफनेस बोलोगे, अगर ये स्ट्रेस स्ट्रेन कर्व है तो फ्रैक्चर पॉइंट तक के एरिया को आप बोलोगे मॉडुलस ऑफ टफनेस. आर यू गेटिंग द पॉइंट और नॉट? नेक्स्ट इज हार्डनेस. हार्डनेस इज सिंपली द एबिलिटी टू रेसिस्ट स्क्रैचेस और टू रेसिस्ट वियर एंड टीयर्स. इट इज नोन एज द हार्डनेस. Okay, don't be confused between toughness and hardness. Okay, all the tough material cannot be hard, or it can be hard, vice versa. Okay, so hardness is all about to resist scratch. You can say that hardness is to resist wear and tear to scratches and all, whereas tough is you can say it is giving you protection against the impact loading. More tough material will bear impact loading, but hard material is good against the scratches and all, but it may not be good in taking impact loading. So this may happen. So this is the difference between the toughness and hardness. Are you getting the point or not? Tell me. Okay, so now what all are the stress strain curves? Suppose if a material is elastoplastic. Elasto means linear behavior. Plastic means okay. If your material is elastoplastic with strain hardening, so if it is elastoplastic with strain hardening, so this is elastic. Stress is proportional to strain. Okay, and it will be coming back after unloading. And if it is with strain hardening, then this will be going like this. Instead of perfectly plasticness, it is going to show some strain hardening. Means beyond elastic limit, your material will be taking more stress along with the strain. Okay, if it is ideal rigid material, then doesn't matter how much force you are applying, so there the strain is always zero. In ideal rigid material. Are you agreeing? Ideal rigid means strain is always zero. Doesn't matter how much stress you are applying. Continuously you are increasing stress but no increment in the strain. Are you getting the point or not? And what would happen in ideal fluid? Ideal fluid without any normal force, you are going to have continuous inflow, or you can say continuous strain. Is it clear? Any doubt in these four graphs? Anybody? Any doubt? चलिए आगे बढ़ते हैं. So these are the stress strain material for some other materials, like curve for some other materials. Like this is quite famous curve, you know, it is mild steel. This is mild steel. Okay. And what about aluminium? Aluminium is like this. Aluminium is like this. This is aluminium. You can see that it is going to like this. And this is the stress strain curve for rubber. This is the stress strain curve for rubber here. And this is for glass, this is for cork or wood, this is for cast iron. Okay, so you can see all these graphs, and this graph is literally important because you can have some relative questions of Young's modulus and all. More strong is the material, more it's Young's modulus. Okay. So nearly you can see the Young's modulus of cast iron, it is not cost, it is cast iron, is half of the that of steel, and the Young's modulus of aluminum is 1/3 of steel. Concrete Young's modulus is 1/10 to 1/20 of steel, depending upon the grade of concrete, it ratio varies, and of wood or cork it is 1/8 to 1/20 of steel. So here we have written each Young's modulus in terms of steel because steel Young's modulus is quite famous and it is very much used in our civil engineering. So steel का Young's modulus तो हम लोग बहुत यूज करते हैं. क्लियर है कि नहीं है? कोई डाउट किसी को यहाँ तक? Anybody? कोई डाउट? Okay. Now what all are the elastic constants? What all are the elastic constant? Okay. So total 4 elastic constant are there: E, G, K, and mu. And we are going to see the interrelationship between them. We will also be going to see the interrelation between them. E is known as Young's modulus. It is the ratio of longitudinal stress to longitudinal strain. G is known as the shear modulus. It is known as the ratio of normal shear stress to shear strain. K is known as the bulk modulus. It is known as the ratio of volumetric stress to volumetric strain. U is known as the Poisson's ratio, which is the ratio of lateral strain to longitudinal strain. Okay. So Young's modulus or modulus of elasticity, it is denoted by E. It is the ratio of normal stress to normal strain under the effect of uniaxial loading. Okay. Uniaxial loading means only in one direction. Only in one direction you are going to apply this. Uniaxial loading in only in one direction you are going to apply this. It is not necessary that always the lengthier side is going to be the axial side. It may happen that in some cases you are going to apply force like this. Then here Young's modulus would be the change in dimension along this with respect to its original dimension. Okay. So Young's modulus is always along the longitudinal axis. Similarly, that shear modulus or you can say modulus of rigidity is there. So what does shear modulus of rigidity? So modulus of rigidity is simply the shear stress upon shear strain. It is the shear stress upon shear strain. Now if I am talking about the bulk modulus, so bulk modulus is how much? Bulk modulus is how much? It is the volumetric stress upon volumetric strain. It is the volumetric stress upon volumetric strain. Okay, so this is the bulk modulus. So you know what is happening in bulk modulus. In bulk modulus you are applying stresses in the multiple direction, like hydrostatic forces and all. This is the case of bulk modulus, or This is the case of bulk modulus due to this volume changes and all. Okay. So in fact, bulk modulus value or strain in the volumetric direction you can calculate as per the strain in the x direction, y direction and z direction. Okay. So this is the Poisson's ratio. It is the ratio of lateral strain to the longitudinal strain under the uniaxial loading. So suppose if you are pulling this body, then its a dimension, let's say this is L and this is B. So when you are stretching it, then it is coming out to be, then it is coming out to be then it is coming out to be what? And it is uh, P minus dP. Okay, yeah, del B. So dear, here the longitudinal stress, longitudinal strain is how much? Here longitudinal strain is delta L over L. Here this is what? Lateral stress is minus, or simply strain is dB over B. So Poisson's ratio is defined as the ratio of lateral to longitudinal. So one thing is positive, another is negative. So in order to make it positive, we will use the negative. Or simply, generally, if one side is compressive, another is tensile. So in order to make it positive, we will be keeping here a negative sign. Okay, we will be keeping here the negative sign. So this is the expression for the Poisson's ratio. So जिस डायरेक्शन में आप फोर्स लगा रहे हो, that will come the strain in that direction will come in the denominator, और जो साइड आपके across है, that side will come in the numerator. Obviously this value would be less even if the direction of load is reverse. So more impact will come here and compression will happen along the perpendicular side and its consequences would be less. So that is the reason why the value of Poisson's ratio is less than 1. Okay. Normally for engineering material this ratio lies between 0 to 0.5. For engineering material it is going to lie between 0 to 0.5. But if you are even considering the polymers and biological elements sum, then it may vary from -1 to 0.5. Okay. Is it clear? So it happens like this. Okay. तो ऐसा भी हो सकता है ये बायोलॉजी. वैसे इंजीनियरिंग मटेरियल के लिए अगर आपसे पूछा जाएगा then you have to take in 0 to 0.5. Okay. So here is some Poisson's ratio value. Cork है ना, कितना होता है कॉर्क का? 0. ग्लास, concrete, elastic material, steel, aluminum, perfectly plastic material, human tissue and soap, it is negative. जैसे बोला ना बायोलॉजिकल मटेरियल, पॉलीमर्स के लिए भी कितना होता है? नेगेटिव होता है ना. सो दिस इज अ वे टू फाइंड द इलास्टिक कांस्टेंट. So you can have a rough idea of this. So if human tissues or polymers etc. are not used, if you are talking about perfectly, if you are talking about the engineering material, then it is 0 to 0.5. Okay. And you know due to this 0 Poisson's ratio, cork is used. Okay, we'll discuss that sometime later. So cork is going to show many unique property due to the 0 Poisson's ratio. Means no change in the lateral direction along with the longitudinal direction. Okay, if you are making changes in the longitudinal direction, so no impacts are coming in the lateral direction. Okay, so these are the important relation between the elastic constant here. These all are the very important relation between the elastic constant between E, G and K. You can see this. अगर आप इन दोनों इक्वेशनों में से ई निकाल दोगे देन सॉरी म्यू का वैल्यू निकाल के प्लेस कर दोगे देन यू विल बी गेटिंग इट दिस. But let me tell you, if you are comfortable with these two equations, then you can solve each and every problem. No need to remember these two values. No need to remember these two values. Okay. No need to remember these two values if you are able to remember these two first two expression. If you want to calculate E based on K and G, so based on K and G you can find the value of mu. You can substitute mu from one equation and you can substitute to the other. Okay, and here you can see K, G and mu are available, so you have to eliminate E and you have to replace the value of E to another material. Okay, it is like this. Okay, so now if axially loaded member, they are axially loaded member. What are axially loaded member? Where we are going to apply forces along the axis. So what is happening here? If my member is axially loaded, then deflection is going to be PL upon AE. As we know that stress is proportional to strain, longitudinal stress. What is longitudinal stress? Force upon area, and it is equal to the constant, and constant you know it is Young's modulus. What is strain? So delta is equal to PL upon AE. So this is the normal deformation in case of uniform section. And if it is a stepped bar, then what to do? If it is a stepped bar, then we can see that total deflection here will be deflection in 1 plus deflection in 2 plus deflection in 3. What is 1? Deflection of AB plus BC plus C. Anybody, what is the deflection of AB? Anybody, what is the deflection of AB? See, simply you have to cut a section where you want to find delta, and you need to check the net force. So you can see at net force with section 1-1, it is P1, it is P1 going out. For section 2-2, for section 2-2, what is the net force? So P1 is outside and P2 is inside, so P1 minus P2, and it is happening for length L2 upon A2 E2. Similarly, for section 3-3, guys, you can see that it is P1 minus P2 plus P3 into L3 upon A3 into E3 upon A3 into E3. Are you getting the point or not? Tell me. Are you getting the point or not? So this is a stepped bar. Okay. So now we can also find the deflection due to rectangular tapered bar or the circular bar. So let me show you. Suppose if rectangular tapering is being done in one direction like this, थोड़ा अजीब सा बन गया, एक मिनट रुक जाओ। अब ठीक है, अब ठीक है। Now it is perfectly all right. Here Let's suppose this thickness is constant. Thickness. समझ लो tapering कैसी है? It is not bidirectional. It is unidirectional. So tapering is unidirectional here dear. It is not bidirectional. ठीक है. और मान लीजिए यहाँ पे width है B1 और यहाँ पे width आ रही है B2. इसका यंग्स मॉडुलस E है और लेट्स सपोज आप इसका एरिया लगा रहे हो, फोर्स लगा रहे हो P और यहाँ पे भी जो फोर्स लग रहा है दैट इज P. So anybody what is the deflection here? Anybody what is going to be deflection here? काफी फेमस एक्सप्रेशन है और यूज भी होता है ये. Circular one, rectangular tapering, circular tapering, all these are used in a very widely manner dear. तो जरा बताइए क्या होगा. ठीक. So here the deflection is equal to P L upon AE. E तो एज इट इज रख दो. नाउ व्हाट इज A? A हम कितना लेंगे? A भी हम लेते हैं, वो लेते हैं weighted average, sorry logarithmic average. Okay, so what is logarithmic average here? Who is varying here? Width. Thickness is constant, so I can write thickness as it is. Now for width I can write it like B1 minus B2. It is the logarithmic average upon log of B1 by B2. Log of B1 by B2. Okay dear, generally we use three types of averages in mathematics. One is arithmetic average, okay, second is geometric average, third is logarithmic average. Okay, arithmetic average where the things are proportioning linearly or in the directly manner. Geometrically where the things are varying geometrically, means the difference between two consecutive values are increasing rapidly and they can be cached by some common ratio. Okay, third is logarithmic where the variation is like inverse, in inverse manner. Here area is coming in the inverse, so it is in inverse manner variation. Okay, yes, Anurag is absolutely right. It is T into B1 minus B2 upon log ln B1 upon B2. Had it been a case of circular tapering beam, if it is a case of circular tapering beam, in that case anybody what we could have write? Suppose this is my circular tapering beam, then what we could have written here? Suppose this is a diameter 1, this is diameter 2 and length is same, and again it is subjected to same tensile load. Let us call P and P. So anybody, what is the expression of deflection dear? What is the expression of deflection? So delta here is again PL upon AE. So what is A we can calculate here because the diameter is varying square times, geometrically times. So here we can take the geometric average of the diameter. So if one value of diameter is D1, if on another end the diameter is D2, then what is the geometric mean or geometric average? So geometric mean of two variables, two quantities are A into B under root. Three quantities geometric mean is A into B into C cube root. Okay, four quantity geometric mean is A, B, C, D raised to the power 1 by 4. Like in arithmetic mean of 2 mean A plus B by 2, 3A plus B plus C by 3. Okay, and this is the logarithmic mean of 2. Are you getting the point or not? Tell me. So this is AE. So what is A? It is pi by 4 into D square. But instead of D square we have to take the geometric average. So it is under root D1 D2, and square of under root D1 D2 is D1 into D2. Okay. So delta here is coming out to be 4PL upon pi E D1 D2. So this is the expression of deflection in case of circular tapering. This is circular tapering, and rectangular tapering is logarithmic average. Yes, Anurag is right. Okay, so okay, already we have discussed such cases. Already we have discussed such cases, and Yeah, this is left. What is the deflection of conical bar due to self weight? Anybody? What is the deflection of conical bar due to self weight? What is the deflection of conical bar due to self weight? Anybody? This is a cone. So what is going to be deflection? You can consider the unit weight of this cone is gamma. If gamma is unit weight of cone, and let's suppose the length of this cone be L, length of this cone be L, and diameter of this cone, or you can say, let's say R. So what is the deflection due to self weight of the cone? What is the deflection? It is simply gamma L square upon 6E, where E is the Young's modulus. Please remember this equation. It is gamma L square upon 6E. Or if you want to calculate it in terms of self weight, then it is as similar as, like, gamma is what? It is weight upon volume. Okay, gamma is what? It is force, weight upon volume. What about volume? Volume is pi by 3 into pi r square h. Okay, so 1L and 1L will cancel. So 1 by 3 pi r square. How much is this? Into 6. So this is 1 by 3 pi r square into h. So if this is the case, then it can be written W L, and this is pi r square is area. Okay, pi r square is area, so it is 18E and all. So if you are going to solve this, so 3 into 2 pi r square area into E. So you can also write delta like this. It is WL upon 2AE. So deflection of conical bar due to self weight is WL upon 2AE. And here it is not by 3, it is by 2 only. Yes, Anurag is right. It is by 2 only. Okay, and same thing happens, Sachin, it is 1 by 2 only, na? Same thing happens in case of rectangular beam, dear. अगर ये rectangular beam का केस होता, ये तो चलो conical हो गया, अगर ये rectangular भी होता, तो rectangular beam में due to self weight क्या आता? It is gamma L square upon 2E, और gamma is equal to ये हो जाएगा weight L square upon volume. Volume कितना हो जाएगा? area into L into 2E. L or L cancel, so answer is coming WL upon 2AE. So it is again half of self weight. It is due to the half of self weight. It is also due to the half of self weight. Okay, so rectangular, conical, and here as well rectangular tapering and circular tapering we have seen. Rectangular tapering and circular tapering we have seen. Okay, so Poisson ratio is minus lateral upon longitudinal. This we have seen already. Acha, now what are the temperature stresses? From class 11th onwards, dear, we have seen in thermodynamics that whenever we are going to increase the temperature, the length, area as well as volume of the object changes. अगर ये टेम्परेचर बढ़ रहा है तो ये चेंज आपका पॉजिटिव है. अगर ये टेम्परेचर कम हो रहा है with respect to the standard temperature, then these changes are negative. Okay, if I am talking about the linear expansion, then incremented length of any dimension can be written as, it is delta L is equal to initial length alpha delta T, where delta T is the difference in temperature, and this difference you can calculate either in degree Celsius or in Kelvin. Alpha is known as the coefficient of thermal expansion and L is known as the initial length of the material. Okay, so if you simply want to check how much your material length has been incremented or it is decreased, then it is L alpha delta T, isn't it? So you can compare the coefficient of thermal expansion of various material. So like copper, brass, aluminum, steel, if we are going to compare, then you can see out of these four material, aluminum is going to have the highest coefficient of thermal expansion, then brass, then copper, and steel is going to have least coefficient of thermal expansion. There is one more beauty of steel here, that steel, the coefficient of thermal expansion exactly matches with the concrete coefficient of thermal expansion, and many of you might be knowing that this is the reason that why steel is very widely used in concrete. Okay, प्रीति जी कह रही है सर अगेन बता दो. प्रीति, I have simply said that थर्मल स्ट्रेसेस क्या होते हैं. तो थर्मल स्ट्रेसेस बताने से पहले मैं आपको ये बता रहा था कि हाउ यू कैन फाइंड द चेंज इन लेंथ. So change in length due to temperature is equal to original length into coefficient of thermal expansion into change of temperature. ठीक है, मान लीजिए कि आपका टेम्परेचर 30 डिग्री से एकदम 50 डिग्री हो गया. आपने बिल्डिंग बनाई 30 डिग्री पे और आज जाकर के उसका टेम्परेचर 45 डिग्री हो गया. ठीक है, तो होगा क्या, मटेरियल इस 15 डिग्री के डिफरेंस के कारण अपनी बेंचमार्क वैल्यू से अपने डायमेंशंस को इंक्रीज करेगा. वो इंक्रीज करेगा, कैसे करेगा ये भी डिपेंड करेगा मटेरियल के ऊपर. अलग अलग मटेरियल के अलग अलग कॉन्ट्रैक्शन एंड कंप्रेशन पावर होती है, एक्सपेंशन पावर होती है. सो उसकी वेरिएशन ऑफ डायमेंशन विद रिस्पेक्ट टू टेम्परेचर की डिग्री को नापने के लिए वी आर यूजिंग कोएफिशिएंट ऑफ थर्मल एक्सपेंशन. ओके, सो विद रिस्पेक्ट टू द इनिशियल वैल्यू इट इज अल्फा इनटू डेल्टा टी. एक्चुअली बोला जाता है कि थर्मल स्ट्रेन are simply alpha delta t. And what is thermal strain? Thermal initial change in dimension due to the temperature upon original dimension is equal to alpha delta t. So change in dimension is equal to L naught alpha delta t. So just I am comparing the value of alpha of different material which we commonly use in strength of material. It is for copper, brass, aluminium and steel. Copper, brass, aluminium और steel के लिए हम use करते हैं. So diffraction of conical bar is equal to 1/3 of the prismatic one. हाँ, ये आप कह सकते हो कि डिफ्लेक्शन ऑफ कॉनिकल बार इज इक्वल टू दी 1/3 ऑफ द प्रिज्मेटिक बार, ये आप बोल सकते हो. बट आपने सेल्फ वेट बाय 3 लिखा था. आपने देखो सेल्फ बाय 3 लिखा था सचिन पहले, इसलिए मैंने आपको ऑब्जेक्ट किया. ठीक है, हाँ आपने पहले सेल्फ बाय 3 लिखा था इसलिए मैंने उसको गलत बोला. इट इज सेल्फ बाय 2 ओनली. Yes, if we are comparing it with respect to the rectangular, then it is 1/3. Yeah, obviously. आप देख सकते हो यहाँ पे, मैं दोबारा दिखा देता हूँ आपको. ये 1/2 है, ये ऐसे देख लो 1/2 आ रहा है, ये 1/6 आ रहा है. So 1/3 times of rectangular. This you can say. Okay. चलो. So these all are the coefficient of. Is it clear, dear Preeti? सचिन क्लियर. अच्छा ठीक है. अच्छा ये है हमारे अलग अलग मटेरियल के कोएफिशिएंट ऑफ थर्मल एक्सपेंशन. मतलब जब टेम्परेचर चेंज होगा तो सबसे ज्यादा इंपैक्ट इन चारों मटेरियल में कौन दिखाएगा? एल्युमिनियम, फिर उसके बाद ब्रास, फिर कॉपर, फिर स्टील. तो स्टील का कोएफिशिएंट ऑफ थर्मल एक्सपेंशन इन चारों में कम है. ठीक है. अच्छा, टेम्परेचर बढ़ेगा तो आपकी लेंथ भी बढ़ेगी, आपकी विड्थ भी बढ़ेगी, आपकी हाइट भी बढ़ेगी. तो जनरली होता क्या है कि ड्यू टू द चेंज ऑफ टेम्परेचर योर ईच एंड एवरी डायमेंशन चेंजेस इफ इट इज फ्री टू डू सो. अगर कोई रेस्ट्रिक्शन नहीं है तो टेम्परेचर बढ़ने के कारण डायमेंशंस चेंज होंगे, और बढ़ने के कारण डायमेंशंस बढ़ेंगे, कम होने के कारण डायमेंशंस कम होंगे. ओके, इफ द डिफॉर्मेशन ड्यू टू टेम्परेचर चेंज इज रिस्ट्रेन्ड देन स्ट्रेस विल बी इंड्यूस्ड. ओके, और नॉर्मली इन इनडिटर्मिनेट स्ट्रक्चर अगर देखो मैं यहाँ पे एक बार लगाऊं, मैं कहूं कि यार यहाँ पे मैंने टेम्परेचर बढ़ा दिया, बट दिस टाइम द मटेरियल इज नॉट फ्री टू एक्सपैंड. नो डाउट ड्यू टू द इंक्रीमेंट ऑफ स्ट्रेस, इंक्रीमेंट ऑफ टेम्परेचर, दिस member would be trying to elongate itself, but it is not getting proper surface. So when those thermal strains which would have been there if it would be free, then those temperature strains or thermal strains will be leading towards your thermal stresses, dear. Will be leading towards the thermal stresses. So whatever would have been the thermal strain, now the thermal stresses originated would be in that manner. Suppose earlier the thermal strain developed was 2 units. Now when those 2 units strain is blocked, the stresses will develop accordingly. Suppose if earlier strain developed in thermal was 4 units, now the stresses developed would be double of that. It would be relative. ओके तो या तो टेम्परेचर बढ़ने के कारण डायमेंशंस बढ़ेंगे, अगर आप डायमेंशंस बढ़ने नहीं दे रहे हो देन करस्पॉन्डिंगली स्ट्रेसेस आएंगे, तनाव आएंगे आपके मटेरियल के अंदर, ठीक है। सो दीज आर नोन एज द थर्मल स्ट्रेसेस. So practically we can see that the amount of thermal stress produced is proportional to the thermal strain which would have been there in case of determinate structure. But in indeterminate structure, wherever there is a restriction in the expansion and contraction, there the interference of temperature stresses comes. Are you getting the point or not? Tell me everybody. ठीक है. अगर मैं ये पूछूं आपसे, अच्छा इसको ना कुछ लोग कंफ्यूज भी हो जाते हैं, ऐसे गलत समझ लेते हैं मतलब, ठीक है। मैं पूछूंगा कि यार यहाँ पे मैंने टेम्परेचर बढ़ाया तो स्ट्रेन होगा, हम बोलेंगे हाँ होगा, कितना होगा, एल अल्फा डेल्टा टी के बराबर होगा। स्ट्रेस होगा, नहीं होगा, क्यों नहीं होगा, क्योंकि जितना स्ट्रेन आया था वो सारा का सारा उसको होने के लिए जगह मिल गई, ओके। तो फिर बाद में बच्चे क्वेश्चन करते हैं, सर आपने तो कहा था कि जब थर्मल स्ट्रेन हो जाता है तो स्ट्रेस नहीं होता, और अब आप कह रहे हो कि सर थर्मल स्ट्रेस थर्मल स्ट्रेन के बराबर होता है। तो प्लीज डू नॉट कंफ्यूज हियर। अगर मटेरियल डिटरमिनेट है तो थर्मल स्ट्रेन होता है, थर्मल स्ट्रेसेस नहीं होता। अगर मटेरियल इनडिटरमिनेट है तो डायमेंशन चेंज नहीं होते, मतलब थर्मल स्ट्रेन नहीं होता बट थर्मल स्ट्रेस होता है। बट इस केस में मैं आपको बता रहा हूं कि थर्मल स्ट्रेस कितना होगा। थर्मल स्ट्रेस उतना ही होगा, उस हिसाब से होगा जितना थर्मल स्ट्रेन हो सकता था अगर ये स्ट्रक्चर फ्री टू एक्सपैंड होता। आर यू गेटिंग द पॉइंट और नॉट? Okay, so same thing I have repeated twice or thrice, but this concept is really very useful. Okay, so thermal stress is no doubt they are proportional to the thermal strain, but thermal strain are in different condition, are in free condition, whereas thermal stresses are developing in the restrained condition, in indeterminate structure. Okay, so normally if temperature increases in a fixed beam, then it is nature of stresses are compressive. Normally if temperature reduces with respect to benchmark temperature, then originally it would have tried to contract, but now no contraction is possible, then you can say the thermal stresses induced here are tensile in nature. Are you getting the point or not? So in case of composite bar, whenever we are having two composite bars attached together and they are also fixed, let's suppose this is copper and let's suppose this is aluminum. Let's suppose this is aluminum and we know that the coefficient of thermal expansion of copper is more than that of aluminum. अभी मैंने आपको यहाँ दिखाए थे, देखो कॉपर का 16 और एल्यूमिनियम का 13, सॉरी कॉपर का 16 स्टील का 13, दूसरा मैंने क्या ले लिया, सॉरी स्टील कर लो इसको यार, स्टील कर लो, एक कॉपर ले लो एक स्टील कर लो। तो स्टील का जो थर्मल एक्सपेंशन है वो कम है और कॉपर का ज्यादा है, तो अल्फा 1 इज ग्रेटर देन अल्फा 2। Now अगर I am going to increase the temperature here, now I am going to increase the temperature here, then what would happen, tell me, in both the materials? अब दोनों मटेरियल में क्या होगा, देखो ना 1 बढ़ पाएगा ना 2 बढ़ पाएगा, बट दोनों की टेंडेंसी होगी बढ़ने की। तो अब होता क्या है, मैं आपको हिंट दे देता हूं, देयर वुड बी ए मटेरियल विच इज बी इन टेंशन एंड देयर वुड बी ए मटेरियल विच वुड बी इन कंप्रेशन। सो टेल मी व्हाट वुड हैपन, tell me what would happen, anybody? चलिए आप बताइए, मैं थोड़ा सा पानी पी लूं। So Sachin has attempted, he is saying कि sir alpha 1 increases more as compared to alpha 2 material. Okay, agreed. But fact is that कि ये स्ट्रक्चर मेरा इंडिटरमिनेट है, बढ़ कोई भी नहीं पाएगा। हाँ, अगर ये स्ट्रक्चर फ्री होता तो कॉपर की लेंथ बड़ी हुई होती, कॉपर की लेंथ बड़ी हुई होती और स्टील की लेंथ भी बढ़ती, पर उतनी नहीं बढ़ पाती जितनी बढ़नी चाहिए थी। कॉपर जितनी नहीं बढ़ पाती। ठीक है, तो ये था मेरे पास, ये मेरे पास कॉपर है, ये मेरे पास स्टील है, ये मेरे पास कॉपर है और ये मेरे पास स्टील है। But the fact is this, that we are not allowing our material to expand, not at all. So what would happen? क्या होगा? Yes, संकेत मानिक इज राइट कि कॉपर पे स्ट्रेस ज्यादा लगेगा, और स्टील पे कम लगेगा। कॉपर पे स्ट्रेस ज्यादा लगेगा और स्टील पे स्ट्रेस कम लगेगा, क्योंकि कॉपर की टेंडेंसी ज्यादा थी एक्सपेंड होने की, तो ज्यादा थर्मल स्ट्रेन हो सकता था वहां पे, तो अकॉर्डिंगली थर्मल स्ट्रेस वुड बी जनरेटेड। Although the value are also depending upon the Young's modulus, because thermal strain is known to you, then also accordingly you can find the thermal stresses, because somewhat you can say that your thermal stresses are E times of thermal strain. Okay, stress are proportional to strain and their connection is based on the elastic modulus or Young's modulus. Are you getting the point or not? Tell me. Are you getting the point or not? Tell me, dear. Okay. One more question I would like to ask. Please answer that with common sense. This is quite clear. Now listen to me. ओके, चल संकेत, चलो मैं आपके क्वेश्चन पे वापस आता हूं, बट अभी आप मुझे बताइए कि अगेन कॉपर एंड स्टील आर एयर एंड आई हैव इंक्रीज्ड द टेम्परेचर, नाउ व्हाट वुड हैपन? आई हैव इंक्रीज्ड द टेम्परेचर, नाउ व्हाट वुड हैपन? टेल मी। दे आर बोथ ऑफ दीज मटेरियल आर कनेक्टेड विद ग्लू, इन दोनों के बीच में परफेक्ट बॉन्डिंग है, इसको किसी रिएजेंट से चिपका रखा है हमने। अब क्या होगा? Here you can see both of the member will be experiencing compression, but if they both are well connected together and it is free to expand in one direction, then tell me what would happen here. And let me talk over Sanket doubt. सर मैंने SOM में बस सिंपल स्ट्रेस स्ट्रेन एंड SFD BMD पढ़ा है, एग्जाम इज रियली क्लोज, shall I study some more small topics from SOM for GATE? Yes संकेत, आपको कुछ टॉपिक्स और पढ़ने चाहिए इफ यू कैन, लाइक ट्रांसफॉर्मेशन ऑफ स्ट्रेसेस और डिफ्लेक्शन, ये दोनों आप पढ़ लो। ट्रांसफॉर्मेशन ऑफ स्ट्रेसेस एंड डिफ्लेक्शन। और स्ट्रक्चर हो रखा है आपका? स्ट्रक्चर आपका हो रखा है संकेत? अच्छा, ही इज सेइंग दैट द सेक्शन विल हॉग, ओके। On copper, Sachin is saying on copper compression will be experienced and on steel tension would be experienced. Okay. See, you can check it like this. What would happen if copper and steel acted independently? What would happen if copper and steel acted independently? So the tendency of copper was to expand more. So copper would be expanded more. Copper would be expanded more and steel would be expanded less, but one thing is sure, both would have been expanded. Okay, Let's say their original benchmark was somewhere there. This is their original length. So since the alpha is more for copper, it will expand more, and alpha of steel is less relative to copper, so it will expand less. So reality में क्या होगा? They are going to have some common settlement point. So you could have seen that your copper is still it could have expanded this one, but it is only expanding till here. So it is experiencing compression. But originally steel could have gone till here only, but it is also now at this level only, because copper and steel are well bonded together. So it will be experiencing the tensile stresses. Like Sachin said कि सर कॉपर पे कंप्रेशन होगा, स्टील पे टेंशन होगा. Very well said. Okay. So whenever we are increasing the temperature of the composite system, where the one thermal expansion is more than that of another, then the one which is having higher coefficient of thermal expansion would be in compression than the other, if I am talking about the increment of temperature. And anybody, what would happen if instead of increment I am talking about the decrement? Suppose if increase of increment I am talking about the decrement, then what would happen? Anybody? What would happen? Anybody? Tell me the cases here. Tell me the cases here, dear. सर स्ट्रक्चर में भी फ्यू सिलेक्टेड टॉपिक किए हैं, गेट में वेटेज कम है, दैट्स व्हाई. डिफ्लेक्शन ऑफ बीम में टोटल 6 मेथड्स हैं, सो विच वन शुड आई डू फर्स्ट? अच्छा चलो ठीक है यार, जब अब संकेत करते हैं डियर बात, आप एक बार ग्रुप पे आ जाओ, फिर देखते हैं, बात करते हैं. वैसे आप वो कर लो डिफ्लेक्शन ऑफ बीम में ना, you guys can proceed with strain energy method. अगर एक ही करना है तो strain energy method कर लीजिए, ठीक है. चलो कोई नहीं, मैं एक जनरल सेशन लूंगा तो उसमें आपको थोड़ा गाइड कर दूंगा कि व्हाट ऑल आर हैपनिंग. ओके ठीक है, चलिए कोई नहीं. अच्छा इधर देखो, if it is a case of temperature decrement, then both would be trying to contract, so both will be feeling tension. दोनों में टेंशन फील होगा, क्योंकि अगर ये फ्री होते तो ये यहीं आके सेटल हो जाते और this are expanding like this. But if it is a case like this, where alpha 1 is more than alpha 2 and there is a decrement of temperature, then copper will be decreased more as compared to steel, because changes would be happening less here. So settlement would be in here, somewhere here. So now the copper would original position of their composite section is here. So now the copper will be here and steel will be like this. So steel would be experiencing compression and copper would be experiencing tension. So this would happen. So like Anurag says, Sachin says that copper में tension होगा सर और steel में compression होगा. So very well said. Okay, so that is the case here. Tell me. Any other doubt? Any other doubt, dear? So this is the way to tackle the composite bars. This is the way to tackle the composite bar. Okay, चलिए आगे बढ़े. So now we will be moving to the next phase here, which is SFD BMD, which is the SFD and BMD. See, this is our total objective today. This is the total objective today here. This one, this one, this one we have completed. So SFD BMD I would like to start now, but if you say then we can take a 5-minute break. Are you all agreeing? 5 मिनट का ब्रेक ले ले. Tell me. So we will meet at सर 1:30 पे क्लास क्लोज्ड है. अच्छा 1:30 पे क्लास क्लोज कर दें फिर हम. ठीक है, वैसे अनुराग भी सही बोल रहे हैं कि सर 1:30 पे क्लास क्लोज कर देंगे. सो आई वॉज थिंकिंग टू टेक ए ब्रेक एंड कंप्लीट SFD BMD in a one go. But yes, what I will do? I will do some portion of SFD and BMD now. Okay, at least theoretical point I will complete now, and after that, from 2 p.m. I would be doing some numericals on SFD BMD, and then we will be doing the remaining subjects. Okay, so let's continue now. ठीक है, हाँ ठीक है. आइडियल कोई चीज नहीं होती. चलो कोई बात नहीं, हम थ्योरेटिकल एस्पेक्ट खत्म कर देते हैं. सो नाउ फर्स्ट ऑफ ऑल आई वांट टू टेल यू दैट फॉर स्टेबिलिटी the total number of reactions should be 3. And we have to make sure that reactions should not be parallel and they should not be concurrent. Okay, and if reactions are parallel, then rigid body deformations can happen in the linear direction, and if reactions are congruent, then rigid body deformations can happen in the you can say rotational direction. Like I want to say you that suppose if this is my beam, and I have 3 reactions, but these 3 reactions are parallel. Suppose these 3 reactions are parallel, so it can show you some rigid body deformation in the x direction. No doubt here you are having 3 reactions, but still it is able to move. And if you are talking about the congruent, then this is the case. What is congruent? Congruent are when the reaction meets at a common point. So this is the congruent point. So here you can see that here the rigid body deformation will happen for inclined load or for horizontal load, and here the rotation would happen about the SO point. So this is rotational motion. Okay, and here it is linear motion. So doesn't matter we need 3 reactions. The point is that 3 reactions must be non-parallel and non-congruent. Because reactions are parallel, then linear instability will be there, and if they are congruent, then rotational instability will be there. And similarly for 3D structure, this is for 2D structure. For 3D structure, we need at least 6 number of reactions for stability, and these 6 reactions should also not be parallel, should also not be congruent, as well as they also should not be coplanar. So those 6 reactions should not be parallel, congruent, as well as should not be non-coplanar, should not be coplanar. Okay, like before starting the SFD BMD, so we have to see what are the various types of beam which we can encounter. So you know this is cantilever beam. So cantilever beam is, this side is fixed, this side is free. So what is the degree of what is the total number of reaction at fixed end? Anybody? What is the total number of reaction in fixed end? So fixed end can resist each and every kind of force. It is a normal force, horizontal force, as well as movement. Okay, so free end is not going to take any force. It is free only, and it is going to show you in fact all possible degree of freedom. This node is going to deflect in the x direction, it can deflect to the y direction, as well as it can show you some theta z. Yes, similarly dear, if I am talking about this propped cantilever beam, simply supported beam, this B beam is simply supported beam, Then here one end is roller and one end is hinge. So hinge support is going to have two supports, one vertical and one horizontal, and roller support is going to carry only one support. And if I'm talking about the degree of freedom, then here theta z can happen, and here as well theta z along with the delta x can happen. So there are 3 degree of freedom and 3 reaction. Here as well 3 degree of freedom and 3 reaction. Okay, if I'm talking about the probed cantilever beam, then what will are the number of reactions here? What will are the number of reactions? Here the number of reactions are 1, 2, 3, 4, and what is the degree of freedom? Degree of freedom would be delta x and theta z. So 2 degree of freedom and 4 number of reaction. Okay, so actually we can identify, we can calculate only up to 3 reactions in 2D system by using the equation of equilibrium. We do have total 3 equation of equilibrium for the static body, that is summation of fx is equal to 0, summation of fy is equal to 0, and summation of mz is equal to 0. Okay, so these 3 are the bodies. Okay, so dear, similarly if I'm talking about the fixed beam, then fixed beam are going to give you how many reactions? 1, 2, 3, 4, 5, 6. Degree of freedom would be 0. Here the degree of freedom would be 0. Okay, so similarly here as well reactions would be 1, 2, 3, 4, 5, 6, 7, 8, and degree of freedom would be delta x, theta z, like this. Okay. 4 is what, dear? 4 is what? Okay, so it is happening like this. So but in strength of material we primarily focused on forces, and that too we are talking about the determinate structure. Now what are determinate structure? Determinate structures are those structures which can be solved only with the help of equilibrium equation. They do not need any additional equation like compatibilities and all. Okay, so they are linear displacement, there are some linear displacement relations, compatibility relations, but those relations are not needed in determinate structure. Once again I am saying that they can be solved only with the help of equilibrium equation. For analyzing structures like indeterminate structure and all, we use structural analysis. So there we have multiple approaches to solve such structure. We can check the degree of freedom of the structure, we can check the total number of unknown forces in the structure. Accordingly we can select the appropriate method to analyze such structure. Okay, but that is a separate session, that is a part of structural analysis. Right now we are restricting ourselves to strength of material only, where we have to analyze some basic structure, some basic determinate structure. It may be cantilever, it may be simply supported, or it may be any determinate structure where at most 3 unknowns are there. And even if the unknowns are greater than 3, then we might be having some add-on equations to analyze such structure. So the key point is total number of unknown forces and total number of available conditions are same in your determinate structure. That is why they are known as determinate structure. Determinate का मतलब होता क्या है? Determinate, which can be determined. Okay, आप उसको निकाल सकते हो, determine कर सकते हो. और you can say they all are the solvable structure. उन structure को आप determine कर सकते हो, उन structure को आप solve कर सकते हो. Now the thing is, what all are the things which need to be solution, which need to be solved there? कौन कौन सी चीजें हैं जो सारी की सारी आपको solve करनी है? वो चीजें हैं forces, वो चीजें होती हैं डिग्री ऑफ फ्रीडम. बट अगेन यहाँ पे हम लोग बात करते हैं फोर्सेस की. तो यहाँ पे वो फोर्सेस को हमें सॉल्व करना है, दोनों लेवल पे सॉल्व करना है. एक्सटर्नल लेवल पे भी करना है, इंटरनल लेवल पे भी करना है. कि एक्सटर्नली आई शुड आल्सो नो कि मेरे को जो एक्सटर्नल रिएक्शन रखनी है वो किस कैपेसिटी की रखनी है, और इंटरनली आई शुड आल्सो नो कि व्हाट आर द वेरियस पॉसिबिलिटीज ऑफ द डिफरेंट स्ट्रेसेस. Okay, accordingly I need to provide the material, accordingly I have to provide the depth of material, cross section of the material, like that. Okay, so that is the reason why the analysis of internal and external force is very, very important. So normally external force we do find by using the equation of equilibrium, static equilibrium, but internal forces study करने के लिए we need to know the concepts of shear force, bending moment and axial force. Because this shear force, bending moment and axial force are nothing but the propagation of this external action within your structure. And you will be able to identify that for which particular location some particular stress function is having the critical value. So these all are the significance of shear force diagram and bending moment diagram. Okay, shear force is basically, shear force diagram is showing you generally in the diagrammatic form the variation of shear force. Bending moment diagram is going to tell you with from diagram point of view the variation of bending moment, and axial force diagram is also going to show you the axial force variation along the length of the beam. Are you getting the point or not? Tell me, all of you. Okay. So this is the significance of shear force and bending moment. Suppose if this is a beam, and let's suppose this is a simply supported beam like this, and here I am applying some point load, let's say P. So you know what is the reaction here? Reaction here would be equal to P by 2 and P by 2. If this is a length, let's suppose this is L by 2 and L by 2. If I am asking you what is the bending moment here, so bending moment here is equal to 0. If I am asking you what is the bending moment at here, you will be saying it is the load into displacement, it is PL by 4. It is the same PL by 4, it is PL by 8. So if I am asking you which is the most critical condition, then what will you do? Rather than finding the bending moment at each and every point, what you will do? You will simply draw its diagram. You will say P by 2 into X, X belongs to 0 to L by 2. So it is going to vary like this. And it is going to vary like this. So this is your BMD. So now just by inspecting this diagram, you will be able to tell others that yes, this is the location where bending moment is most critical and this is the center point. Okay. So if you want to make this structure safe in bending, then your you can say your benchmark should be PL by 4. Okay, जो आपकी तैयारियां होंगी वो PL by 4 के लिए होंगी. Accordingly, you will be designing your section. Are you getting the point or not? So this is the benefit of drawing, significance of drawing diagrams. Suppose if I want to make the diagram for shear force, then shear force as well it is P by 2. Okay. And it is also P by 2 like this. So you can say that yes, the critical condition for shear force here is P by 2. If you want to make your structure safe in shear, then you would be designing it for P by 2 shear. Like in RCC you used to did. अभी हमने RCC का मैराथन किया था, वहाँ पे shear पढ़ा था, तो shear के लिए critical value भी हमें पता होनी चाहिए, bending के लिए भी होनी चाहिए. Basically this is for your flexural design, this is your for shear design. Okay, so all these are the significance of SFD and BMD. Okay, so how to plot SFD and BMD and what are the definition and exact procedure, I will be discussing from 2 o'clock, and for that I will be using a different link. तो इस क्लास को मैं भी बंद ही कर देता हूँ, ठीक है. तो इस क्लास को मैं बंद कर देता हूँ और स्टार्ट करूंगा मैं SFD BMD के प्रोसीजर से, ठीक है. एक और मैं आपको बना के दिखा दूंगा SFD BMD कैसे बनेगा सब लोगों को एक बार, और एक दो एग्जांपल भी समझा दूंगा. एंड आफ्टर दैट वी विल बी डूइंग द अपकमिंग टॉपिक्स, ठीक है. तो लिंक वुड बी सेपरेट फॉर दैट क्लास. आई होप यू ऑल हैव दैट लिंक, ठीक है. इट वुड बी एंड गेम मैराथन सीरीज SOM-2, ठीक है. चलो मैं ग्रुप पे आपको दोबारा भेज दूंगा. एंड इट विल बी स्टार्टेड फ्रॉम 2 PM. 2 बजे इसको स्टार्ट कर देंगे हम लोग, ठीक है. 2 बजे इसको हम लोग स्टार्ट कर देंगे, ठीक है. सो लेट्स हैव आवर लंच ब्रेक, एंड आफ्टर 40 minutes आई एम एंडिंग दिस सेशन ओनली, एंड आफ्टर 40 minutes we will be starting our session number 2, and we will be continuing from here. हम यहाँ से ही कंटिन्यू कर रहे होंगे, ठीक है. But yes, I want to remind you some important things that do not forget to enroll yourself for AIMT. Live mentoring product is there with all the new iconic subscription, and special class we will be planning today at 10 PM dear. And you guys can check out the brand new updates on Unacademy Ask a Doubt, which is the faster and better way to solve doubt. This is our official Telegram channel, and You can see that all these are the benefits of our Plus and Iconic plan. Although we have lot many free content on Unacademy official YouTube channel as well as Unacademy special classes, but still I recommend my learners to go for this. So guys, all these are the subscription prices in Plus and Iconic, and thanks a lot. Take care. So we will be meeting again in link number 2. I will be sharing that link in the group. Okay, till then, bye bye.